truss that holds the secondary, and they can work on the instruments from this catwalk inside the dome. And here's a picture when they're opening up at night. I've just been so lucky being able to visit all these observatories. I've kind of been, since the beginning, doing the technology transition of the adaptive optics and laser guide stars in particular. I've had basically an open door at all these observatories, and it's just a great deal of fun and really kind of awe-inspiring. And today I get real excited every time I see a new discovery that's been enabled by this technology. But it's what's really interesting in these big observatories is they're like cathedrals. People are whispering and they're being very reverent, around all this stuff, because we're kind of unlocking the secrets of the universe here. So it's kind of interesting. The other thing adaptive optics is being used for is solar astronomy. Now here we aren't using laser guide stars. We're actually doing image correlation between little cells to run the adaptive optics. So these are pictures made from southern New Mexico at the solar observatory down there. And here's an example with and without adaptive optics. So there's been lots of science. What I like to point out is in the beginning, the SOR had the most refereed, laser guide star AO science papers. And of course now this graph is it was made in the middle of 2012, but it's continuing to go up. And lots of really interesting papers. The astronomers are doing great stuff. Some of these images are pretty old. Here's Uranus and images made with the adaptive optics at 2 wavelengths. And here is like a direct comparison with Hubble at the same wavelength. Here's the Hubble and the visible, and here's Keck and the IR. We're able to now see this was one of the early planet detections in this picture. I thought it was the asteroid with the moon, but it isn't. And one of the greatest studies has been done by a group at UCLA about the black hole in the center of our galaxy. This arrow kind of points to where that is. Of course, you can't see it because, as you know, black holes don't allow any light to escape. But this is at the time, a really high resolution image of that region. 1 arc second here is about this big. And so one time when they were observing, they saw this, a bright flash here. And if you look at the time scale, this lasted over several minutes. So this is material being sucked into the black hole that's being compressed by the gravitational forces. And as it's compressed, it heats up. And the heat is emitted thermally and flashes just before it gets sucked in. So that's kind of like a flash bulb going off. But just think about this a minute. That's 25,000. Well, first of all, what we're seeing here happened 25,000 years ago. And it's 25,000 light years away. That's a really bright flash. So I would say you don't be messing around with this black hole thing. So what they've done is they've mapped the orbits of those nearby stars over about a decade, and by knowing something about the makeup of the stars and their mass, you can now determine the mass of the black hole, and that turns out to be 4 million suns. So that black hole has a mass of 4 million suns.
What is this size relative to our sun?
Well, they say it's much smaller, right? So you got all that mass in a much smaller volume.
Yeah, I mean the physical size.
I don't know. I mean, there's all kinds of theories and cosmological ideas, but and it's pretty hard to prove anybody right or anybody wrong. So here's another comparison with Hubble again at the same wavelength. And this is just because this is a 10-meter telescope that has adaptive optics. We're now being no longer limited by the atmosphere, and we're able to take advantage of the laws of optical physics and use the diffraction limit of a 10-meter telescope versus a 2.4-meter telescope. And we're seeing now, here's a planetary system, one of the first ones discovered in 2008, again by Keck, and it has 3 planets. And so this is, again, this is the result of the coronagraph that subtracts the light from the bright star. The bright star is 10 to the 10th times brighter than the planet. So that's a tough problem. And you know, these are typically, well, here's a half an arc second. So this is really a very high contrast image. So I was going to tell you about what we call ordinary anisoplanetism, but based on the lateness of the hour, I'm not. Basically, when you look off axis from the object that you're correcting, the correction gets worse pretty quickly. And that's because the turbulence a few microradians away from your beacon is different. And so if you have, so here's a binary star, this is with the loop open, these are counts on the detector. Here the loop is closed on this star. Its companion is 35 microradians away. And so you'll notice that if we look at the correction in the direction that we're correcting, it's very good. This is 26,000 compared to 370. That's how much more sensitivity we have now than we did have. Whereas over here, this is the worst, the average, and the best of 100 exposures. It's not nearly as good. So this is a limitation of ground-based adaptive optics unless you do something called multi-conjugate adaptive optics, which we don't have time to talk about. But it's basically, you use multiple deformable mirrors and multiple guide stars, and you make a 3-dimensional map of the turbulence above the telescope. And you use that 3-dimensional map to do corrections in any direction you want. And that's been implemented on the 8-meter telescope in Chile, where they have 5 laser guide stars, 3 deformable mirrors, partridge, and a parakeet. And here's an example image, which is 9/10 of an arc-minute square. Now you say that's not a very big field, but that's a huge field in astronomy. And they're able to, they have quantitative measurements on these stars in the edge of the field, and they've now extended this to 2 arc minutes, and it works really well. So, here's an example. This is that Gemini planet imager that has the 4,000 actuator coronagraph. And so here are 3 planets around this star, and here are the spectra of 2 of those planets. Nothing to indicate life, but they're different. So we're already beginning to see the beginnings of evolutions of planets. So the next step are these giant telescopes. Here's the 30-meter telescope that they want to build on the big island of Hawaii on Mauna Kea. It has 492 1.4-meter mirrors, segmented mirrors, hexagonal mirrors. And each one of these mirrors has a separate harness on the back that corrects for gravitational effects. As it rotates from the horizon to the zenith, you know, it undergoes different gravity. And so the mirrors are fairly thin, and the effects of gravity cause those mirrors to bend and change their shape, but that's corrected by this warping harness. And I should have shown a picture of the one that they use at Keck. Keck has 36 segments. This one has 492. And it has these enormous, these platforms on the side of the telescope. There's a tertiary mirror in the middle. Light comes down to the primary, up to the secondary, off the tertiary into these instruments. And all of these instruments are being built with adaptive optics built in. So this telescope would not have been built without this technology.
So the Hubble, for example,